Welcome to another video on digital electronics. In this video we'll be seeing what is a multiplexer tree. So say if I have to implement a 32:1 mux using two 16:1 mux, then how do we do this? This problem arises when we have some hardware available but we want to create something that is larger than the availability. So I do not have a hardware for 32:1 mux, but I have to somehow create it using a 16:1 or maybe say 8:1 or it could be 4:1, anything. So here we'll be seeing an example of using two 16:1 mux. So as we know, 16:1 mux, 2:4 gives us 16, right? So I have to have 4 select lines to create that 16:1 mux. So see here, we have two 16:1 mux. This is one 16:1, this is second 16:1, and I have 4 select lines, S0, S1, S2 and S3. Same other select lines here also. But to create a 32:1 mux, I require 5 select lines because 2:5 is equal to 32. So I have to add additional select line which will control these two mux. So first mux is from 0 to 15, the second mux is from 16 to 31. So if you consider the first value 0 to 31, which are in total 32 values, so we are implementing a 32:1 mux. Let's see how it works. For this you have to make a truth table to understand better. So these are my 5 select lines for 32:1 because 2:5 is equal to 32. So 5 select lines, it will go from 0, 0, 0, 0, 0. Next will be 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, and so on. I will not write all the 32 values, but giving you an understanding of how it works. So somewhere I will get 0, 1, 1, 1, 1. If you remember 0 all ones, this is nothing but 15. This is 0 value. This is 15 value. After this, for 16th value, I will write 1, 0, 0, 0, 0. Why? Because E is 2:0, 2:1, 2:2, 2:3, 2:4. And 2:4 is nothing but 16 value. So decimal number 16 is 1 and all 4 zeros, right? Similarly, this will continue. After this I will have 17, which is 1, 0, 0, 0, 1, and so on till my last value, all 5 ones. This is nothing but 31. So if you add 2:0 is 1, plus 2:1 is 2, plus 2:2 is 4, plus 2:3 is 8, plus 2:4 is 16. This should give you 31. So 16 plus 8, 24, plus 4, 28, plus 3 gives you 31. So my last decimal number for all ones is 31. If you see this truth table, it is very clear that at exactly half of the values, 0 to 15 and then 16 to 17, my all A's are 0 here and my all A's are 1 here. And if you consider this block, this entire block of B, C, D, E, this entire block of B, C, D, E is exactly getting repeated here. B, C, D, starting from 0, 0, 0, 0 to 1, 1, 1, 1, and here also 0, 0, 0 to 1, 1, 1, 1, which means I will use same select lines for B, C, D, E, and which is what we have done here. I have S0, S1, S2, S3. So my S3 is B, C is S2, D is S1, and E is S0. So what about A? We will give some control to A in such a way that at a given point of time, A is either 0 or it is 1. If it is 0, one mux will work. If it is 1, another mux will work. So at the enable, if you see this G, this is nothing but enable. So enable of these two are connected with A, but it is having a NOT gate here. By doing this, what we are doing is, if I give G as say 0, for which G1, if I give this as 0, this will, being active low, this will get enabled. But since this is 0, if this is 0, then after a NOT gate I will get a 1 here, which means this will be inactive. So at a given point of time, this will be active, this will not be active. In other case, if I give a 1 here, which means this is not active. A 1 will become after NOT gate a 0 here, which is active low, and this will become enabled. So at a given point of time, out of the 2 mux, only 1 mux is going to work. Rest of the things will be taken care by B, C, D, E. So for example, let's write an example here. I say I want this value of 17. So for 17, my A will be 1. So if A is 1, after NOT it becomes 0, which means this second mux is active, this mux is active, and 0 0 0 1, B, C, D, E, 0 0 0 1. So 0 0 0 1, 0 0 0 1 is nothing but 1. So considering this as a 16th one, for which all my BCD were 0 0 0 0, next will be 17, for which my BCD value is 0 0 0 1. So this value will get selected. So whatever is available at 17 will appear at this output. That is what mux is, right? Depending on the select lines, depending on the code of the select lines, whatever is at the input, I will have at the available at the output. So if at 17 I have 1, I will have a 1 here. If at 17 I have a 0, I will have a 0 here. Fine. So I have my output of 17 available here. What about this? Since this is 1, this is not active, I will have a 0 here. So I have a 0 here and a 1 here. What is OR going to give you? It's going to give you obviously 1. So on the code of 1 0 0 0 1, at 17 if I had 1, I got a 1 here at the output. So for OR, I have 0 here because this is not enabled. I have a 1 here because at 17 I have 1 and I have select lines as 0 0 0 1. So it will connect to the first input. This is the 0th, 16th is the 0th input, 17th is the first input to the second mux. 0 and 1, my output is 1. Say I had a 0 here. Say at 17 I had 0 here. So I will get a 0 here because my select lines are still 0 0 0 1. So whatever is at 17 will appear here. For both 0 and 0, my OR will again give me a 0, which means the input of 17 is getting reflected at the output. So that is the beauty of the OR gate. What does an OR gate tell you? 0 0 0 1 1 0 and 1 1. 2 input OR gate. If both are 0, the output is 0. If 0 1, I have output 1. I'm sorry. I will rewrite the truth table. 0 0 0 1 1 0 1 1. For 0 0 output is 0, for 0 1 it is 1, and for all it is 1. Now say one of the input is always 0 because this mux is not working, right? So say this is the mux whose output is 0. This will never be the case because one of the input is always 0, so both 1 are never possible. If one of the mux is not working, if this mux is not working, then see, is it reflecting the output of the second mux value? 1 here and 1 here. So is it reflecting the output of the second mux value? Yes. And hence OR gate is important here to pass on the input at the input values to the final output, because this is the intermediate output. This output and this output are the intermediate output of the individual mux. Because we are creating a 32:1 mux, which should have one output and 32 inputs. So if I consider a larger scale, then this entire box from right from here to here, this entire blue box which I have created, this is a 32:1 mux having 32 inputs and one single output. So this is how we implement a multiplexer tree. You can implement using any number of muxes, it doesn't matter. Currently we are using 2:16:1. You can also use 4:8:1 or 8:4:1. The output still and the logic still remains the same. So I hope this is clear. I will stop the video here. Thank you for watching.